Hi, this is Team 2, and this is our submission for the introductory project. So for this project, we processed the in-phase and quadrature samples collected from the Pluto for specified target frequencies. Then we used Fast Fourier Transforms to visualize the frequency and constructed spectrograms to visualize the target spectral band with respect to time. This was done using the inbuilt SciPy function specified on the slide. So now we're going to go over the Python source code. So lines 1 through 8 was when we were importing all the relevant libraries we would need for this project. We then defined and set the sample rate, center frequency, and buffer size. These parameters were changed depending on the wireless transmission we were looking at. Then in the next section, we configure and set up the radio, so creating an object of the Pluto radio. After that, we create an array of received data, which is then passed to the spectrogram function. The spectrograms are generated using the inbuilt SciPy function. This function computes a spectrogram with consecutive Fourier transforms, so it takes in specified parameters like the time series of measurement values. It then returns three outputs: the array of sample frequencies, the time indices, and the spectrogram. We also included the offset to get plotting above and below the frequency, the center frequency. In the final part, we plot and format the spectrogram with the y-axis being time and the x-axis frequency.
All right, so the first signal we looked at was a DTV, or digital TV signal. We used the website TV Fool to figure out what the strongest DTV signal near campus was, which turned out to be channel 29 or Univision. It's about 9 miles from campus. Channel 29 is between 560 and 566 megahertz, so carrier frequency of 563 megahertz was used. The bandwidth of the signal was 6 megahertz. The spectrum that resulted can be seen on the right and matches with the expected spectrum for the DTV signal down below, where you can see the orange arrows match up with the ATSC pilot in the spectrogram on the right and the ATSC pilot in the spectrum on the bottom. Then the second signal we found was a GPS L1 band signal. The L1 band is the oldest GPS frequency band, so it's the most widely used. The carrier frequency we used for it was 1,575 megahertz. The bandwidth we used was 20 megahertz, so that's what the parameters were. The spectrum that resulted can be seen on the right, and that matches the spectrum that's seen below. The big lobe in the middle is visualized with the orange arrows. You can see the bright orange line on the spectrogram on the right corresponds with the highest peaks in the spectrum on the left. Then there's two more kind of greenish bluish lobes, which are the two red arrows in both the spectrogram on the right and the spectrum below. And then the receive strength slowly drops off until it becomes purple.
The next signal we looked at was a ham radio signal. This is a single side broadcast style of transmission. So you have a carrier frequency and then the data on one side of the carrier frequency. So on the graph on the left, you can see how there's a spike and then it kind of drops off very sharply on one side and slowly on the other. And on our spectrogram on the right, you can see the bright yellow line of the carrier frequency and then the much dimmer kind of blue of the weaker signal on one side of the carrier frequency. For this, we used a bandwidth of 521 megahertz because that's the lowest the Pluto can go, even though the actual bandwidth for a ham radio transmission is much, much smaller. The next signal we looked at was a pager. These are between 929 and 930 megahertz. Older pagers use amplitude modulation, so we believe that that is in fact what we have right here. As you can see, there are well-defined chunks of a high-powered or yellow signal and then a slightly darker, less powered blue chunk of signal. We believe this was from St. Vincent Hospital, but we're not 100% sure. And then the last signal we looked at was a cell phone tower signal. And you can see on the right how the signal is divided up into like large rectangles. Those are the resource frames of a 4G LTE signal. We believe this is from the Verizon cell tower on WPI's campus. And that's our project. Thank you for watching.